I don't know what happened there. I thought I did start the meeting, but apparently it decided not to do this. Okay. Yeah, I see people now. Sorry about that. I thought I had started the meeting and Zoom seemed to be working, but apparently it wasn't, or it crashed or something. Yeah. Yeah, we've mostly just been reviewing what I did in the last class, so you didn't miss much. Only a couple of things I would say are that announcements that I had was that we won't have group meeting, office hours today, and to please bring your laptops for Friday because we are going to hopefully start doing some quantum program, laptop or tablet, so that we can access the quantum service. Oops. Something went wrong with that animation there, but it's important. Okay. All right. Yes. Okay. So controlled U gate now. Okay. So we've stopped talking about C naught gate. Any questions on C naught or that proof that I did using QWERT? Have people been playing around with QWERT? I'm just curious. Have you found it useful too at all? No, not really. Okay. Maybe I need to give you something that would make you use it. But I found that, we'll anyway be doing quantum programming, and at some point it's just easier to use the IBM quantum composer and do it there on their machines. But of course, it's good to check it with the simulation with QWERT or something. Okay. Certainly, before you spend a lot of time running a big quantum simulation, which costs money. I mean, not for you guys because you're an education program. But eventually, it will cost a lot of money if you're doing it professionally. Then you want to check some of the basics at least on something, either with your own code or using QWERT or something like that. Okay, so our next gate is called the controlled U gate. U meaning can be any unitary operation on a single qubit. Okay, so all of the unitary gates that we have learned earlier for single qubits simply become available now as a control gate, okay, or control U gate. So it means it applies the quantum gate U to the right qubit if the left qubit is 1, okay? So, for example, CU acting on the state 0, 0 will give me 0, 0 because nothing has changed. Similarly, CU acting on 0, 1 will give me the state 0, 1, but CU acting on the state 1, 0 will keep 1 the same, but use the matrix or take the gate U and apply it to the right qubit. Okay, and similarly, it'll take 1, 1 and apply U to the right qubit, which is in the state 1. So that will be the action of this qubit. Here, for example, from IBM Composer, you can create some generic U. Remember, U in when we learned about single qubit gates can be specified by a bunch of angles and phases. And so if you cast your mind back, there are at least, with theta and phi, for example, and 1 gamma, and for an external phase, you can create any U that you want in the qubit space. So you can do that in the IBM Quantum Composer. They have an extra degree of freedom for amplitude or something. And that allows you to then take this left qubit, and if it is 1, operate that on the right qubit. Okay. So as an example, this is just one that I came up with because it's a very important gate in measurement-based quantum computation and also in several other protocols for quantum teleportation and so on. This measurement, this control Z gate is used in measurement-based quantum computation. Remember, casting your mind all the way back to lecture 1, there are at least 4 different architectures for quantum computing. Measurement-based quantum computing is one of them. And you can use this gate to prepare so-called graph states, which are useful for measurement-based quantum computation. Anyway, so what does the Z gate do? Well, of course, the Z gate acting on single qubits is very simple, right? Z acting on the state 0 does nothing. Z acting on the 1 state gives you a minus sign on the 1 state. Okay. So now let's think what would be the matrix for this control Z gate with the 2-qubit system. Do you want to try and work that out and tell me? Let's try to think about that for a second. Ahead, go back here. This is the action of any general control U gate. The Z gate puts a minus sign on the 1 state. So what does the matrix of the control U gate look like? Yes? Were you going to say something? Yes.
Does it just look like, I don't know how to best describe it.
Yeah, sure.
So 3 identity matrix kind of looking like this.
Yeah.
1, 0, 0, -1.
Okay, let's write it up. PU, you say, is
This was for CC.
CC, sorry, CC, correct. Yeah.
So 3 identity matrix. So 1001
1001.
there, and then bottom left. Top right.
1001 here and 1001. Okay,
And then the bottom right, identity matrix kind of, and the bottom right one is negative. The 108.
okay. So that is the claim. So how do we know if he's right? Yes.
Test it.
Test it. How do I test it?
Try it with 0001.
Excellent. So let's do it on 00. Okay. So what does this matrix on 00 give me?
Zero, 0, +1.
Gives me 00 plus 10. Everybody see that? Okay, if not, let's do it. So 1001, 1001, 1001, 100 minus 1, acting on the state 00. Right? The 00 is the column vector 1000, right? Agree? Okay, so that is 1010 acting. So I multiply it by 1, multiply this plus these two, these two, these two. So I get a 1, which is good. Okay, operating in the same way, you see that it's always the first element or the first column that is going to come out. So 10. Is that what we expect for the CC acting on 00? What do you think? You were the one who suggested this.
Yeah, I think.
Yeah. Okay. Great, excellent, exactly. So this is how you go about it, right? If you came up with something because you quickly, came up with a suggestion for what it should be. Well, this is how we check it, and we immediately see, okay, and now we know how to fix it too, right? Okay, so obviously I need zeros here, right? A 0 here, that's a 0, okay? And similarly, you can argue that the next one must also be a 0 down here because I want 01 to stay as 01, right? So we have fixed 2 columns of the matrix. Now we have to fix the third column, right? What should the third column be? Yes.
0, 0, 1, 0.
Very good. 0, 0, 1, 0. And what about the last one? Do you have your address? Yeah, I thought you had your address. Sorry. Okay. Yes.
0, 0, 0, 1.
Yes. Very good. Okay. That's exactly right. Okay. Does everybody see this? If not, please stop me so that we can go over it. Yes,
Can you just go through the last column?
the last one?
Yeah.
Yeah. Right, this is our matrix. And now the state 1, 1, which is what we want for our final. Okay, so let's look at this one. So 1 multiplying the first row, this first row multiplying this gives me a 0. Right? Second row multiplying this also gives me a 0. Third row multiplying this column, again all zeros because the only non-zero element is this one, and that's multiplied by a 0. And so we are left with this last row, and that will give me a -1. So this gives me the state in Ket algebra form minus 1, 1. Okay. So if I were to summarize everything we've written in Ket algebra form, CZ acting on Ket 0, 0 gives me 0, 0. PZ acting on Ket 0, 1 gives me 0, 1. CZ acting on the Ket 1, 0 gives me 1, 0. And CZ acting on 1, 1 gives me the state minus 1, 1. So we can see then that any superposition CZ acting on the state A 0, 0 plus B 0, 1 plus C 1, 0 plus D 1, 1 gives me A 0, 0 plus B 0, 1 C 1, 0 minus D 1. And again, in column vector form, this would be identical to saying PZ acting on any general state, any general column vector in the 4 dimensional space or the 2 qubit space is going to give me A, B, C minus D. Okay. Any questions on this? I think this is another exercise here. And now we can do any general. Oh, sorry. I'm not hearing any questions, so hopefully everybody is on the same page. Yeah, I think by now you'll be able to get this one. Suppose any general U, I take any general U, right? U acting on the state 0 is A 0 plus B 1. U acting on the state 1 is C 0 plus D 1. Okay. So what is the matrix for U? U acting on, yeah.
I do the same thing we did last time, just like the bottom right.
No. Before we go to control U, let's just talk about the matrix for you. Just two qubit, 1 qubit 2D matrix, 2 by 2 matrix. What is that? Yes.
A, B, C, D.
Yeah. A, B column, C, D column. Everybody okay with that? Hopefully you're starting to see these connections a little bit more intuitively now. If not, yeah, keep working at it, it'll come. Okay. All right, now let's move to what were you saying, Anish?
So the control U, last time we saw we wanted like zeros for all the corners except like the bottom right. So we can kind of just put that matrix in the bottom.
And the bottom right, and then what's on the top left?
Left. Just the same thing we had last time, which is like
Huh?
It should be identical.
Identity. Very good. Yes, exactly. Okay, so that was a bit of, talking about it, so it's always easier to write it down. So the matrix U for 2D, or for single qubits is this, right? Because of the way we defined it. And therefore, CU, as pointed out by our esteemed colleagues, is 1001. So on the top left, we have an identity matrix. On the off diagonals, we have zeros. So zeros. And then down here, we have A, B, C, D. How can we know if this works? Obviously, we test it. Okay. So, okay, I won't do the cases of, CU acting on 0, 0 is going to give me 0, 0, clearly, because there's just one element here. CU acting on 0, 1 is also going to give me 0, 1. So those two are hopefully right away. You can read that off. And so the only thing we want to know is what does it do to the states 1, 0, and 1. We can read that off as it gives me A times 1, 0 plus B times 1, 1. Is this what we expect? Well, let's look at this. So CU acting on the state 1, 0 should give me the state 1 for the left qubit, tensor with U acting on the 0 state. Okay, right? And U acting on the 0 state was simply tensor A at 0 plus B 1, which gives me A 1, 0, B 1, 1, which is what we have here. Okay, so and similarly for the last column. Okay, now we know how to write all of those. Any question on this before I move on? Do you know how to do the last one on your own? Yes? The last column. That is CU acting on 1, 1. What do you think that will give me? So, picking on you.
D.
D.
Like so.
Since I called on you, let me do it. Or at least let me write down your answer. Okay, if you don't know or can't work it out in your head, what would you start by doing? How would I work out the action of CU on the last state 1, 1? By the way, did you follow why I got this to begin with? Okay, so how do I go from that to this one?
That's my it's like
Yeah.
I'm thinking about like the vector.
Yes, very good. Exactly. And what is the vector for 1, 1?
0, 0.
Excellent. So it's 0, 0, 0, 1. And then on here is that matrix that we wrote. And so what you should just know is that I'll take each of these rows and multiply it into these columns, right? Okay, I guess I should just write it down. It's easier than walking. So when I take each of these rows and multiply through the column, we see that the output is going to be 0, 0, right? And then out of in this row, the only element that's picked out is C, right? And in this row, the only element that's picked out is D. So this in the Ket language will be written as C 10 plus D 11, which again, going back to here, is exactly what you would expect because it's CU acting on 11 is 1 time tensor with U acting on 1, that's 1 tensor, etc., as we wrote down on the slide, and that will give us the same answer. Okay, we've gone through several of these. I know it seems, for some of you, it may seem like it's, repeating the same point, but I hope if we do it enough times, now you start to get that intuition, like many of you are starting to get that. What will happen when you take any general control gate, write the matrix. Okay. We now introduce one more gate, which is also very commonly used. This is called the swap gate. Okay. And the name suggests exactly what it does. It swaps the two qubits. Okay. So it's very straightforwardly, swap acting on 0, 0 is 0, 0. Swap acting on 0, 1 is 1, 0. Swap acting on 1, 0 is 0, 1. Swap acting on 1, 1 is just 1, 1. The circuit symbol for this is shown here. Okay, as you can see, it has this notation, right? Implying that A is going to B and B is going to A, sort of notation. And you can see that also on the outputs. If I take any two bits, A and B, the outputs become swapped, BB, BA. Okay. Oh, sometimes you'll see it as if they're crossing wires over here. So crossing wires, you have to think that these don't intersect here; they just sort of go over each other. So you can see that if I take two wires and I ran them across, that will be the same as the swap gate, right? Whatever is on the input of A will appear here, input of B will appear here. So one of the things to note about swap is that by itself, it cannot produce entanglement. Even if I put Hadamard's or whatever on it, let's imagine that, if you remember for the control NOT gate, if I had taken A and put a Hadamard, let's say 0 on A, and I put a Hadamard, then I get a plus state, right? And then if I use a control NOT gate, I will get entanglement because the output state will be some kind of entangled state acting on the output because it will be a Bell state or EPR state, like we discussed at the beginning of the lecture and last week as well. But no matter what I do, suppose I put a Hadamard here and some other gate here, whatever they are, okay? Let's say this is a Hadamard, then this is a plus state, and this is let's say this is a minus state. Let's say we put another Hadamard. Well, after you exchange, all it does is make the state still as product states. It's still minus over here, plus over here. There's nothing in between the qubits that's going to affect one qubit based on the state of the other. That's the key requirement that we need for all entangling or two qubit gates that create entanglement. That something in that matrix or in that gate has to affect one of the qubits depending on the state of the other qubit. And as you can see, that just doesn't happen. The two qubits basically don't see each other. They just swap their states, but they never kind of know whether the other guy is in some entangled state or some superposition state or not. It doesn't really understand that. Okay. And you can verify this, for example, again from the matrix. If you took this matrix and you operated it on a product state, you'll end up with product shapes. Yeah, that's fairly straightforward. You can do it yourself with the column vectors. Okay. Yeah, so the effect on any general superposition can be seen using either Ket algebra or linear algebra. I'm not going to repeat it here because I think we've done enough examples that hopefully you can put it together. If you can't, if you're still confused, just come and talk to me. Okay. And here's the matrix form for this. So this is just as we might expect, it swaps the 0, 1 and 1, 0 states, as you can see here. Okay, so 0, 1, if I put 0, 1, which is the column vector 0, 1, 0, 0, okay, you can see that picks out the second column, right? And the second column is the 1, 0 state. When I act on the 0, 1 state. So 0, 1 goes to 1, 0. Similarly, if I take this column, that is the what will happen when the matrix acts on the state 1, 0, because the column vector 0, 0, 1, 0 is the state, the catch state 1, 0, right? The third state in our superposition, in our basis states. And so the third state basically becomes the second state, because the column vector says that there's only a 1 in the second position. So whatever is the third column vector here will become, or the third state will become the second state. So we flip the second and the third states, and the other states are not touched. Is this okay? No? Look a little not convinced.
No, I get it.
Okay, good, excellent, very good. If later you feel maybe you didn't get it, that's okay too. Come back and talk to you. Okay, in Quark, this is located under the half turns section. It's pretty straightforward. Let me just show you. Can people in Zoom see this? I don't know. Oh, it's gone again. Oh my goodness. What the heck is going on? Zoom is missing. Once again. Wow. Hey, it says it's going. This is so weird. Can people on Zoom see me? Hear me?
Yeah.
See people there. Okay. All right. Okay, hopefully you can see and hear me. All right. For some reason it said it was gone again. So, all right, let me share this works. Maybe that was a problem. Okay. So, all right, let's clear all. Okay. And under half turns, as you can see, you see a swap gate over there. So it's right there. So okay. And so that's it. Okay, so we have to move that swap to the 2 qubits that we want to flip. Now, just back up slide here. Right. So let's simulate this circuit. Only the people. Yeah. Sorry.
Sorry, just going back to some
Yeah.
I get how to like apply the gates on the qubits.
Yeah.
I just like for like the Z control Z.
Control Z, yeah.
Like, how do we know that we ended up getting that there was all like the same states except for one, say it was a negative one?
Yeah.
How did we know that that was the result?
How do we know?
Yeah, like that was like what we like how did we know that that's what we, because we were trying to find the key.
Yeah.
Like that was the problem. And so like,
Oh, okay. Maybe you mean you go back here. Here. So control U, in any control U, has this effect on the state. On a catch state. So CU acting on 0, 0 gives me 0, 0, 0, 1 gives me 0, 1, 1, 0 gives me 1 tensor with U acting on 0. And similarly, this one gives me 1 tensor U1. So from this, we can write down what we expect for control C, for example, or swap. Swap can't be written in this way, but the idea is the same. Okay. And then when we check the matrix, we were checking that the matrix indeed gives us what we expect from this definition. Okay.
yeah.
Yeah. And I think I did one example here. So the control U. Yeah, right here. So. Here for control U. So here's control U. Okay. Before I wrote down the column vector, I can write down what control U must do to the states. I can just do that because I know the definition, which is okay, CU acting on 0, 0 does nothing, 0, 1 does nothing. But then when it acts on 1, 0, what it does is it's one tensor U0. And U0 is A times 0 plus B times 1, which gives me this A10 plus B1. And then I can look at what the matrix will do. This matrix acting on the state 1, 0, which is the column 0, 0, 1, 0, gives me the exact same state. That's what I wrote on the top. Does that make sense?
Yeah. We also say like the CZ on 1, 0, say that's like the one state tensor with Z on 0.
Yes, exactly. The same thing. Whatever I wrote for CU is true for CZ.
Okay.
Good. Okay. Yeah, good question. Thanks. Okay, let's go back to the, yeah. Okay, so I wanted to simulate a certain circuit. Sorry, I lost my place now, so I have to go back. What was the circuit? Here it is. Okay. So we want this circuit. Okay. Before we do the circuit, let's just think about what the circuit is saying. Okay. So it's saying the first qubit has a NOT gate on it. Remember, this sign here is like a NOT gate or an X gate. Okay. Same thing. In Quark, at least, they are the same thing. In Composer, as we'll see, they are different, but yeah. They are different symbols. That's all. Okay. So, and then we see a swap operation. Yeah.
Screen share pause.
Jeez.
I think it's because, or,
When I switch between.
yeah, I think they're like PHYS.
Okay, I see. Yeah, that could be it. All right, maybe that's the problem. Thank you for pointing. Okay, we're back here. All right, so coming back to the circuit, before we simulate it, let's try to understand it, okay, which we can do in this simple case. So as I said, 0 will flip over to a 1 due to the NOT gate. And then this is a swap between the leftmost qubit, which is this one here, and the rightmost qubit. So 1 will go over here, 0 will come over here. Okay. And then we have a swap gate again, okay, between the middle qubit and the leftmost qubit. Remember, the leftmost qubit was 1 here. So after the whole swap operation, these two qubits will be 0, and this middle qubit will be 1. Is that okay to everyone? How the circuit works? Okay, so now that's simulated in Quark. I suppose if you're right, I should keep redoing this, which is painful. All right, so we will start with poly gate here. There. Swap. Here. There. Okay. So, and remember, we start with everything in zeros. Okay, that's exactly what we expect. So at the end of the operation, these two are off and this middle one is on. Okay. We can also, of course, do this using the matrices, but that's maybe a little overkill. Yeah, for this particular circuit, it's easy enough to just know what is going to happen. Okay, so let me stop the share here. Go back. All right, and our next claim, this is a circuit identity with swaps. Swap can be created from 3 CNOTs. So often what happens is we may not directly have access to swap. In some cases, it's easy enough, but especially on a superconducting qubit chip, you may imagine, neighboring qubits are somewhat easy to swap, maybe, right? Because they have an interaction between them. But what if I want to swap with some distant qubit somewhere else? Because I can't directly swap the wires between the qubits, right? Like, because it's a planar chip and trying to route wires all over the place would be crazy. We try to like just do adjacent type operations. As an example. And so the swap is an operation that can be created from 3 CNOTs. So if you have a way to like keep doing CNOT, you can build up enough that you can do a swap between any 2 qubits. So you can do this between 2 qubits, and then you can take that one and you can swap it with the same CNOT gates with another qubit further away, which is closer to it on the chip, and so on and so forth. Just as an example of one reason why you want all these circuit identities is that it all depends on the implementation and the hardware, which gates are easy to do and which gates are harder to do, and then you want to simplify the circuit to make it as easy as possible for the computer to run the simulation. Okay, run the code. Okay, so as we can see, working again from left to right here is equivalent to right to left here on the. This is why I was saying you have to be careful about how you read these things. So the circuit goes from left to right, of course, like time flowing from left to right. But the matrices, we want to act first with this matrix, which is the CNOT over here, right? This is CNOT, regular CNOT, 1, 0, if you like, CNOT 1, 0. Left qubit is a control qubit, right qubit is a target qubit. And then we have CNOT 0, 1, right qubit is a control, left qubit is a target. And then the last step again is a CNOT. So it's right to left. It reads the same as this direction. Okay. Again, it's somewhat symmetrical, so probably didn't matter in this case, but you could imagine it will matter. Okay. All right, so here's the proof. This proof is actually comparatively a little bit easier. Of course, we can do it by linear algebra. We can just multiply the 3 CNOT matrices that we have. Okay, and we should verify that that's the same as that swap matrix that I wrote down. So that's something I can leave to you. You can do that in your Python code or something. Here, I want to illustrate a nice proof which just uses the property that CNOTs are controlled XOR gates. Okay. Just so I know, it's CNOT 0, 1, and then CNOT. Okay. Can people in Zoom still hear me? I just want to make sure I didn't somehow stop the Zoom.
Yes, we can.
Good. Thank you. Our claim is swap equals CNOT 0, 1 CNOT. Okay, so the proof is I'm going to take 2 states A and B, okay, as my input. So this A and B can be anything, right? Meaning any bit. right? So there are 4 possible input states, right? That could be here. I have 0, 0, 0, 1, 1, 0, 1, 1. I'm going to treat them all with this proof, just with this method, okay? So the first thing is this C naught over here. What it does, remember, is that it'll send A through because it doesn't affect the control qubit, but the target qubit gets an XOR on it, which is this becomes A with A XOR B. Okay. So we can use the rules of binary addition to understand what will happen next. Okay. All right. The next one is the C naught 0, 1. And what this does is that it leaves this state unchanged. The right qubit is unchanged because that's the control qubit now. And the left qubit gets XORed with the right qubit. So it's A XOR A plus A XOR B. Okay. Everyone okay with this step? Okay. I mean, if I wanted to, I would do this with like 0, 0, 0, 1, 1, 0, 1, 1, and I would have to do it 4 different times to get the same chain of reasoning that I'm just showing you using just symbols. Okay. So that's all it is. Okay, now we use the basic identity that A XOR with A is 0. Okay, with this we can verify, or it's hopefully obvious to you. So there are only 2 possibilities, 0 plus 0, which is obviously 0, okay, and 1 XOR with 1 is also 0, because remember this is binary addition. And so 1 plus 1 is 2, but in binary addition, 2 is equivalent to 0 in this case, okay, for single bits. Okay. Which means that this state over here is a state B with A XOR B. Okay, we're almost there. Okay. The last step is this C naught over here. Okay. But again, that what it does is just like this one, leaves the left qubit unchanged and takes XOR with the right qubit. So B XOR A plus B. And again, by the same argument, B plus B is 0. So this gives me B A. Okay. So that, I mean, yeah, so we have just basically proven the identity that this is the same as swap. We have taken the right hand side and operated on any state AB, which A and B can be 0 and 1. So that's all 4 states, and we have shown for all 4 combinations, it does swap the states. Oh, any questions on the proof? Yes.
Couldn't you, if we're talking couldn't you structure the gates such that actually I'm looking at it now, never.
No, it's fine to think aloud. That's okay.
Yeah, I was gonna ask, can you structure it such that way? Because on Quirk it says that it doesn't affect 0, 0, 1 state. And I took that as they're just identities.
Okay.
Never.
Okay, no worries. Yeah, that proves this identity here. Oh, sorry. Okay, we just did it with so-called Ket algebra, and you can do it with linear algebra by simply taking the matrices and multiplying them. So I won't do that. It's worthwhile doing it. Okay, and sort of the last gate I want to introduce, which is important, is the Toffoli gate. The Toffoli gate is one of the few gates that we talk about that acts on 3 qubit cycles. So remember when I first started talking about gates, multiple qubit gates, I said most of the time all we ever do is talk about 2 qubits. This is the one exception to that rule. Okay. Here we do 3 qubit gate. Okay. So what does it do? Its action is exactly as indicated by the circuit diagram here. It'll flip the rightmost qubit if the left and the middle one are 1. Okay. So again, it's very simple to write this down in Ket algebra notation. Toffoli on A, B, C is equal to A, B, both are unchanged because they are control qubits. And then C is XORed with the product of A and B, because only if A and B are 1 will anything happen to C. Okay. So A, B together is an AND gate effectively between them. So that's the product A, B. It turns out that this gate, I mean, if you think back to like a few weeks ago when we discussed classical computing, I told you about reversible classical computing. Very briefly, but we talked about it. And Toffoli gate is actually coming from classical reversible computing, where it was shown that this gate is universal for classical reversible computers. Okay. And of course, everything that a classical reversible computer can do can be simulated on a a classical reversible computer can do every operation that a normal computer that uses only irreversible gates can do. Okay. It can always give you the same truth table. But except it can be run backwards also. That's important for quantum as well. Okay, so here is the matrix. You can see it's kind of very straightforward. It's just all ones. Everything okay? Just all ones, except right at the bottom here, there's a little X gate over there at the bottom. Okay. So it's a very simple looking matrix, not too bad. And okay, so we can look at this on Quark. Since I'm running a little low on time, maybe I'll do that in the next class. Let's talk about something I think is pretty cool, which is the no cloning theorem. Okay. So yeah, I mean, and of course, by now, hopefully you've seen enough Quark examples that you feel comfortable going and doing this. Maybe I'll assign that as a little homework for you. Verify on Quark that the Toffoli gate acts the way that we expect it to. Okay. All right. So now I'm going to discuss something called the no cloning theorem. This is a very famous and important result in quantum computing. It's a very fundamental, like a deep result. Okay. So let's talk about it a little bit. I don't know if we'll have time for the proof today, but we can at least discuss its statement and the applications. Okay. So the first thing we should say is there are many things that the no cloning theorem does not state. Okay. So let's start with the things that we know we can do. Okay. So this is a result that is true, which is that if I'm given a known quantum state, if somebody tells you, I know what the quantum state is, and I'm giving it to you, we can always create a copy. Okay. So for example, if I told you that my left qubit was in the plus state and the right qubit was in the 0 state, okay, then with the unitary gate, I can go to this state, which is plus plus. What should I do? What unitary gate should I apply here such that the left qubit remains unchanged and the right qubit goes to the plus state? The gate we have discussed. Yes. Liam. Liam, right? I'm sorry. Tristan, sorry, yeah. Yeah. C naught, you say? Well, yeah, so C naught will keep the left qubit unchanged, but what will happen at the output? No, it'll be entangled, right? Because the plus state here and 0 here will give me a Bell state, actually. Yes, at the back. Either one of you, sorry. Yeah.
Is it the Hadamard gate?
It's a Hadamard gate. So what about the left qubit? Whenever I do unitary stuff, I have to operate on both qubits.
Just identity.
Identity, wire, basically. Yeah. So wire or identity on the left qubit, Hadamard on the right qubit. This is actually one of the first gates we talked about at the very beginning when I discussed 2 qubit gates. Okay. It's a type of gate which does nothing. It doesn't create, I mean, it doesn't do nothing, but it doesn't create entanglement, basically, what I was saying. So yeah, exactly. So we know how to do this with a unitary gate. Okay. And that's because we know what the state was. And we always know, given one state on the block vector, on the block sphere for a qubit, we can always go from 0 to that gate with some unitary gate. Okay. So if I know where I am on the block sphere for the state, then I can know what unitary gate will take me there from 0 or 1, etc. So I can always create that state again any number of times. Okay, so I can have a machine which all it does is it takes input zeros and it takes the gate U, acts on the state and produces the unknown, the known quantum state, psi or plus or minus, whatever it is. The problem, and this is really the statement of the no cloning theorem, is we cannot clone or copy unknown quantum states. So the statement is that if I create a unitary machine that takes psi 0, that is, psi is an unknown state. Okay, I don't know what it is. And the right qubit is in the state 0. And if I want to get this state now, basically I've copied psi onto the right qubit, this is prohibited. Is formally, it cannot be done in the laws of quantum mechanics. Okay, so that's a statement of the theorem, and it has some important implications. Okay, well, on the one hand, we can say if you think about any unknown quantum state, we know we can specify it by two complex numbers, right? A and B. Okay, or maybe even more generally, if it's a pure quantum state, it has two real numbers, theta and phi, on the block sphere that's specified. Okay, so knowing two real numbers, right? I can specify any unknown quantum state. But what this is saying is I can't learn what those numbers are, theta and phi. Okay, with just one state. Okay. Now, if I had like a billion of them, of course I can measure. I can keep measuring. So if I have a billion quantum states exactly prepared identically to each other, okay, then what I do is I measure, I get the probability to be in the 0 state, I get the probability to be in the 1 state. Maybe I do some operations to measure along X and Y and so on. And this way I learn everything there is to know about the state with those independent measurements. Okay. So if I have a billion of the same quantum state, then it's okay. I can do the measurement. I can prepare and I can learn what the quantum state is. It's only when I have one of them that I can't learn the measurement, can't learn the state right away. Okay. All right. So that's an important clarification. Oh. Yeah. So it's a sort of a statement of unlearnability of unknown quantum states. It's not, I mean, I'm not making a deep statement here. I think there are some deep research and theorems that people are exploring in this area, but I'm no expert on that, so I won't say much more. The other implication it has, and this is actually a real tragedy for quantum computing, right, is the greatest thing if it would be if we had the no cloning, if the no cloning theorem did not exist, if it was wrong, and we could clone a state many times, is we can run a quantum computer just once, right? And you know, I've talked to you before, quantum computer creates all these massive entangled states inside the quantum computer, right? So at some point, we can stop the quantum computation, and now we are left with some massively entangled state, but we don't know what it is, okay? Right? I mean, I've not proven this, but I've talked to you about it, like why it has its power and so on. And now, if I could simply take that state and make a clone of it a billion times, I can learn what it is. Okay, I can know what that state is. And once I know the state, then I know everything that I need to know, and I can get the answer to my algorithm by running the quantum computer once. Okay. Of course, there's some time required for measurements and so on, but we are not worrying about that at this point. Okay. The point is, this would be super polynomial speed up, right? Because any problem that a quantum computer can solve, which a classical computer cannot, and if I can just run it one time and then learn everything I need to know about the state from there, I mean, maybe even the secret of the universe is hidden there, because as we discussed with 300 qubits, I have more information than the entire entire number of atoms in the universe, right? So this is a very high dimensional space that we could just explore forever, right? If we could do this. Okay, so but we can't do it. That's what the no cloning theorem forbids. And maybe that's a good thing. Maybe too much knowledge would be bad. We'd become like Thanos and try to destroy the universe or something. So the other important or interesting thing about no cloning theorem is that it can have some applications. So there are people who have I'm kind of somewhat familiar with this one, actually. This was one of the original quantum applications. People, when first started thinking about what could quantum be good for, one of the first applications was, what about a quantum money? So you take a currency and you imprint in it a quantum state, right? Then in principle, it can never be copied, can never be counterfeited, okay? And of course, you have to have some protocol to verify that it's real without destroying it. But then you just destroy it and you exchange to the user another, some other state, for example, or some other currency, for example, with its own state. But this is how you could do quantum money and it would be perfectly protected, even better than Bitcoin, right? So yeah, this is an application. This was one of the original applications of quantum. And, there's been some thoughts about what to do with that. But yeah, and also for software protection, if you cannot, create a copy of the software, so to speak, they can't just be written down as lines of code on a screen, then nobody can copy it either. And you can even protect it against viruses and so on, authenticate it perfectly, etc. Okay, anyway, so those are some applications that are on the good side of the no cloning theorem. Okay. All right, I am out of time for today, so we will deal with the proof and in the next class. If you have any questions, I'll be here for a couple.